So my phone is almost out of charge, so I'm unable to see the chat while I'm lecturing in full screen. So if you have any questions, just unmute your mic and speak up. Tell me to stop. Because if you just type and I'm in full screen, I'm not going to be able to see it. Bismillah. Okay, continuing from where we were in the previous lecture, we ended up speaking about, angular momentum and torque. And if you remember in chapter 9, when we discussed impulse, and then we discussed momentum, we said the rate of change of momentum, how quickly momentum changes, is our force. Equally speaking, the rate of changing of angular momentum is the torque, which is, force's cousin, which is force's cousin in angular stuff. So the vector, if we take all the torques, sum them up, like before we took all the forces and summed them up, and then we looked at the time rate change of angular momentum, we end up having the same quantity. Okay, so in chapter 9, sometimes when we wanted to see what is the force and we did not have enough information, but we had information of momentum, we looked at final momentum minus initial momentum and looked at how much time difference there is. And same thing we can do here. And I think the best way to describe something, to describe this, is looking at sample problem 11.04. So we have a half-kilogram particle, and its position is not fixed. It's actually given by a function, r equals minus 2t squared minus t in the I direction, plus 5j, plus 5 in the j direction. We want the angular momentum and torque. Okay, let's start with angular momentum. Angular momentum, we said, is r cross p, which is m r cross v. Okay. We know m, half kilograms. We know r, it's right there. What is v? How can we find out what v is? Anyone remembers?
34R.
What of r? Sorry?
Derivative.
Yeah, derivative of r. Good. So you remember this from chapter 2. Yeah, we take dr by dt and we get v. So dr by dt, we end up with minus 4t minus 1 in the I direction. J was a constant, so it just goes away. We put that back in. We get minus 2t squared minus t in the I direction plus 5 in the j direction cross minus 4t minus 1 in the I direction. I cross I is 0. 5j cross minus 4t minus 1i, we get, what's j cross I? Remember?
K.
I, j, k. I, j, k. So if we do j cross I, we're going in reverse, we get minus k. So minus k, multiply the numbers, we get minus 20t minus 5. But then we have a minus outside, so minus minus is plus. So we end up with 20t plus 5k meters squares per second. To find L, we multiply it by mass because it's mr cross v. We end up with 10t plus 2.5 kilograms meters per second, meter square per second in the k direction. Any questions on this? Cool. Okay. All right. Now we want to find torque. One way is to find force and do then R cross F. Another way, since we already know angular momentum L, we just take the time derivative of that, which is a much easier way because time derivative of that is simply going to be 10. 10t becomes 10, 2.5 is a constant, it goes away. So we just end up with 10 Newton meters in the k direction. Now, since both quantities L and torque are positive, it means it's rotating in the anti-clockwise direction with respect to the origin. Okay. So this is if we try to draw it. At time equals 0, R is at 5j. At time equals 1, it would have moved in that direction. At time is 2, it's going to have moved more in that direction. So it's rotating counterclockwise. Both angular momentum and torque point out of the figure. Okay, because R cross V, so we have R. It's going in this direction, so V is here. My third one is going to be out of the page. Okay, both torque and angular momentum are out of the page. Okay, so far we have been talking about single particles. What if we have a system of particles, more than one? Now remember, with straight lines, we used to deal with single particles, and then we went to rigid bodies and we said, okay, you know what? We can describe a rigid body in terms of its center of mass, right? Position center of mass, velocity center of mass, acceleration center of mass, momentum center of mass, blah, 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 blah. What if we have a bunch of particles that are rotating? Do we have a center of mass equivalent here for angular momentum? Well, to start with, since angular momentum is a vector, we can simply, to find the total angular momentum, we can simply add all the angular momenta. Okay. And just like for one particle, if we do dl by dt, we get torque. For a system of particles, we take the sum of all angular momenta, take the time derivative, we get the net torque. This is very, very similar to F net equals dp over dt. There we used to do everything in terms of linear momentum. Here it's in terms of angular momentum, but the idea is exactly the same. Okay. What if we don't have a just bunch of dots? What if we actually have a rigid body, a fixed object? What if I have this water bottle and I'm trying to rotate it? How do I find its angular momentum? Now, MR cross V is going to be problematic because, as you remember, V is different for each point. So what do we do? هذا الماي مال ولدي ما مالي ما تقول الدكتور ما صايم. So what do we do? How do we calculate the angular momentum of a rigid body? No? Okay. Well, if we look about the axis of rotation, the origin, and I look at a tiny bit of this rigid body. Okay, so I have this whole rigid body. The whole thing is rotating. And I'm going to look at only a tiny bit of it. Okay, I'm going to look at tiny bit of it, of the whole body. It's going to have a mass delta m, tiny bit. It's going to be at some distance, r, from the origin. Only this tiny bit will have an angular momentum, Ri, Pi, right? Mr cross V just for that tiny bit. Now, since we cannot use just Vi for the entire body, we need to express this in terms of something else, something which we can generalize to every part. So V equals R omega. I'm going to put this back in. Ri, Mi, omega, Ri. عندنا حبتين Ri زحمة الدنيا. خلينا نطبقهم في بعض. Omega mi ri squared. What is mi ri squared? You remember?
Inertia.
Yep. So the total angular momentum will be the sum of all these tiny angular momenta, which is going to be omega sum of all the mi ri squareds, which is simply I omega. Which some of you I can hear tell me in your head, زي لو كنت ريحنا من بداية وتقول أنه we can just translate. M becomes I and V becomes omega. Yeah. This is one of the beauties of this whole rotational thing, is that we don't have to learn everything by rote. We already know these things for linear. We just learn the translation of it. Okay. Linear momentum was conserved. Angular momentum also conserved. Okay. Now, if the total angular momentum dl by dt, okay, if the rate of, no, let me rephrase that. If the rate of change of angular momentum, which is equal to torque, is equal to 0, if there's no net torque on the system, what does that mean? It means angular momentum is a constant. If we have an L and d by dt is equal to 0, the only way it is 0 is if L is a constant. So, in the absence of net torque, angular momentum before equals angular momentum after. Li equals Lf. So, ملخص, if there is no net torque, net torque is 0, Li equals Lf. II omega I equals IF omega F. We can remember it from linear. This way. Yeah, same idea. Let's try first thing first. Any questions until now?
No.
Okay. Let's try a PIQ. So I didn't have time to put it into Moodle, so we'll just do it on the chat. A solid sphere of radius r rotates about an axis that is tangent to the sphere with an angular speed omega. Under the action of internal forces, the radius of the sphere increases to 2r. What is the final angular speed of the sphere? Okay, so just type your answer in the chat bar. Okay, we have a whole bunch of A's. Good. Can you still see the screen, by the way, when I'm in full screen?
Yes.
Okay, good.
Yes.
Good. Most of you chose option A, which is indeed correct. So Li equals Lf. I initial, omega initial, I final over omega final. It's a sphere, so I equals 2 over 5 mr squared. So we'll have 2 over 5 mr squared omega I equals, it becomes 2r, so 2 over 5 m 2r squared omega final, 2 over 5, 2 over 5, m r squared goes away. So we get omega I equals 4 omega f. Otherwise, final omega is equal to initial omega over 4. Good. Now I want to show you something, actually. As you can see, that is my son's account. Loads of children's stuff. Okay. So I'll show you some cool videos of how angular momentum works. And then we can go through the physics of it.
China loves U.S. products, but they are not available or expensive.
Doctor, we can't see the screen.
You can't? Can or cannot?
No, we can't. I don't know what happened.
Now can you see it?
Yes, now it's fine.
Okay. So I'll leave you with this video. I'll mute myself. Okay. So what did you notice in these videos? You'll notice that the girl was holding something that is rotating. Now, there were no external forces, nothing to speed her up or slow her down, but by simply changing the direction of the rotation, for example, or something like that, she would end up rotating clockwise, counterclockwise. If she moved it a bit further away, she would go faster, or she would slow down. Okay, and this is an interesting bit about angular momentum. Okay, because just like what we did here, yeah, this was a theoretical thing. Solid sphere, increase r, decrease r. What happened when this girl brought these things out or took them in? She changed r. Her moment of inertia changed. Hence, her angular momentum also changed. She was rotating at a certain speed. Bringing it in, she started rotating faster. Yeah. القطة عندها 7 أرواح. That's something we are used to hearing, since very early days. Turns out القطة ما عندها 7 أرواح. القطة is really, really good with angular momentum. Because when the cat actually drops, it uses conservation of angular momentum. Now, I really doubt she knows the equations, but apparently she can do it without the equations. The cat repositions itself so that when it lands in a certain way as to make the change in angular momentum as smooth as possible. So the impulse would be as little as possible. So, to sort of conclude, okay, what we have been doing over and over again now for the last 3-4 lectures, okay, we will go into a summary. Force, torque, linear momentum, angular momentum, total linear momentum, total angular momentum, linear momentum for a rigid body, mv com, angular momentum for a rigid body, L equals I omega. Newton's second law, F equals dp by dt, F equals ma. Newton's second law for rotational body, torque net equals dl by dt or r cross f. Okay, or I alpha. Conservation, if there's no external forces, momentum is a constant. If there are no external torques, angular momentum is a constant. ملخص مفيد, everything we have done in the last 2-3 lectures. So let's do a sample problem. Let's end this chapter with a sample problem, which I really like, sample problem 11.05. This figure shows a student sitting on a stool that can rotate freely about a vertical axis. The student, initially at rest, is holding a bicycle wheel whose rim is loaded with lead, so the outside is really, really heavy, and whose rotational inertia about its central axis is 1.2 kilograms meters square. Now the wheel is rotating at an angular velocity of 3.9 revolutions per second. in a counterclockwise fashion. Now, what happens is the student takes this wheel and goes. So the student takes this wheel, which was like this, and makes it upside down. Okay, now this is supposed to have a wheel at the end here. Okay, so it's like this, and this thing is rotating, and the student goes like this, and now it's rotating like this. Okay, angular momentum now is reversed because we have made it upside down. Okay, now this inversion results in the student ending up in a circle, rotating. Okay, now once this whole thing is rotating, the composite rigid body, so the student, the chair, that rotating thingy, has a total inertial rotational inertia of 6.8 kilograms meters per second. Okay, what is the angular velocity omega b? What would be the angular velocity of the student? Now this looks like a really complicated problem, but in reality it's actually really simple once we finish reading it. What is the information we know? I wheel 1.2, omega wheel 3.9 revolutions per second. Bring it upside down, the whole thing becomes 6.8. We don't know what omega is. Li equals Lf. So my angular momentum of the wheel plus the body before equals my angular momentum of the wheel plus the body after. Before, the body was not rotating, so angular momentum 0. Later, it will be minus LWH. So later I have LB plus LW. Before I have just LW. Rearrange. LB equals 2LW. Let's substitute. See, so far I have not made any assumptions on the shape or on anything. Yeah, I'm just leaving I. I'm not using mr squared, 2 over 5, 1 over 2, 2 over 3. No assumptions. Omega b would be 2I omega h over IB multiplied by the original velocity of the wheel. If I put in the numbers, I get the person will go in 1.4 revolutions. That's clear? Do you have any questions on this? No? Some of you might be asking on chat. No, nothing. Okay. No questions? Okay. So we are actually ahead of the work plan at the moment. So according to the work plan, today we were supposed to finish until 11.7, but we finished until 11.8. We still have 10 minutes, but I don't want to start chapter 12. You have enough going on. I hear a lot of you have, some tests and some other stuff this week. Okay. Let's keep it at that. On Wednesday, we'll start chapter 12, inshallah, so that all sections are at the same level. This week's quiz will include sections 10.5 to 11.4. So everything we did today, as usual, is not included. It will be simple, nice, just like last week. Okay. 11.9 is not included. 11.9 is not included. It's quite complicated. Okay, it's quite complicated, so we'll leave it out. 10.5 to 11.4. No, 11.5 to 11.4. Okay, nice and simple. Okay. Cool. Wait, 10.5 was already there last, you have a good point. So 10.6 to 11.4, even less. There we go. Okay, so I'll stop recording now.